Okay, so we are going to continue to talk about exponents and exponent rules, but we're going to add in this idea that our exponents don't have to be integers. They don't have to be whole numbers. We've seen that they don't have to be positive numbers. We have negative exponents too. We have 0 as an exponent. We can also have fractions as exponents. So when we talk about rational exponents, right? Rational numbers are numbers that we can represent as a fraction. So 1/2, 2/3, 1/4. 3/8. Those are rational numbers. And we can have exponents that are rational numbers as well. If our exponent is a rational number, what that's actually telling us, sort of in a practical sense, is that I could also write that number as a root. So for example, if I had x to the 1/2 power, that is telling me that what I have is the square root of x. If I have x to the 1/3 power, that is telling me I have the cube root of x. So the denominator for our fraction is what we call the index for our root. For a square root, we usually don't write that little 2 there, but you could if you wanted to. For any other kind of root, a cube root, a fourth root, a fifth root, we would write that little number there. What kind of root is this, right? So the bottom of your fraction, the denominator, is the index for your root. And then the top of your fraction, the numerator, tells you the power that you have, if you have one. So where I just have x to the first, we wouldn't necessarily need to write that. But if I have something like x to the 2/3 power, we definitely need to write the index for the root. And then we would also definitely need to write that we have x squared, not just x. That square can also go under the root, like I've written it here, or outside of the root. Since I would have a power to a power, if I were to represent that cube root as a 1/3 power, power to a power I would multiply, and since we're multiplying, it doesn't matter if the square is inside and the 1/3 outside, or the 1/3 inside and the square outside, vice versa, that means the same thing, okay? So it's a really long way to say these are the same. These mean the same thing. When we're evaluating a particular number, so if I had maybe 8 to the 2/3 power, I tend to look at the root first and then square or do whatever I need to do. So I do the root first because this would be a smaller number before I square it generally, an easier number to work with, especially if we're talking about an integer. So that's my personal preference, but they mean the same thing, okay? So the first thing I want to practice for today is just being able to swap between these different forms. So I have here the square root of 4 cubed. For this first one, I'm going to go ahead and change this root to its exponent version. So where I have the square root, I can write that as the 1/2 power. And then where I've got power to a power, we multiply. 3 times 1/2 would be 3/2. So this would be 4 to the 3/2 power. Nothing is different in this problem because it's a fraction instead of an integer, right? If this were 4 cubed squared, we would multiply the exponents. We multiplied the exponents here. I wrote out a little more work than we normally do, but it's exactly the same type of problem. We're also seeing some problems here where we have numbers instead of variables as the base. It's still the same problem, same type. I don't change anything that I'm doing. If this were an x instead, this would be an x instead, but it's the same idea, same problem. For number 2, same idea. For this one, I'm going to be a little more sort of fluid in my approach here. This would be 2 to the 5th, and then the 3 tells me the denominator for my rational exponent. If it helps you to write it out and multiply, write it out and multiply. But the index for your root is always going to be the denominator for your rational exponent. If you whatever power you have, sometimes it's just 1 and you don't see it, but if you already have an exponent there, that's the numerator, that's the top. And then on our third example here, I've got a bunch of things under the root here. So that means all of these, since they're all under the root, are all to the 1/2 power. I'm going to distribute through this exponent the same way I would if it were a whole number instead of a rational number. So 4 gets that 1/2 power. X cubed, where I've got power to a power, we multiply, so that'd be 3/2. And then y to the 6/2. So these are the same exponent rules that we used last week and earlier this week. What I can do from here, though, is simplify this exponent. 6/2 is just 3. So I have x to the 3/2 power y cubed. And then 4 to the 1/2, we could actually simplify. We know the square root of 4, right? If I forget about all that other stuff, we have the square root of 4, and we know the square root of 4 is 2. So this would be 2. When we're looking at numbers to a rational exponent, again, my preference, it just makes more sense to my brain, is to rewrite as the root 8 to the 1/3 power. Doesn't make as much sense to me as the cube root of 8. This is easier for me to think about than this. If you happen to be that same way where this is easier for you to think about than this, then it is absolutely okay to rewrite in that root form. So that's why you will usually see me rewrite as a root instead of using those numbers as rational exponents. Okay? But if this makes sense to you to be able to evaluate, then that's fine too. So we took our roots and wrote them as exponents. Now we're going to take our rational exponents and write them as roots. We can go one way, we can go the other. So here this would be a cube root of x to the 4th, or the cube root of x all to the 4th power. Those mean the same thing. Our second one here, we've got x to the 1/5 power. So this is a 5th root of x, and it's just to the 1st power. So if you want to write the 1, you can, but we just would have x there. And then x to the 4/7 power. So this is a 7th root of x. We can put the exponent outside the root or keep it inside. Again, they mean the same thing. Questions for me so far? Okay. Now let's do some practice evaluating with our rational exponents. So I've got a few different functions here. Let's start with f. F of 0 means we have 0 to the 1/2 power. The 1/2 power is the same as the square root of 0 to the 1st power, or the square root of 0, which would just be 0. F of 1 means we have 1 to the 1/2 power, which is the same as the square root of 1. Again, I like to see that root version when I'm simplifying with a number. It just makes more sense to me, so I tend to write them out. And then the square root of 1 is just 1. (16 to the 1/2 power would be the square root of 16. Do we know the square root of 16? 4. And then our last example for f, this would be (-16 to the 1/2 power, which is the square root of (-16). And what have we said about taking square roots of negative numbers? It's undefined, or we could say non-real. Undefined, not real. For g, same idea. So we are plugging in values for x. G of 0 would be 0 to the 3/2 power. So that would be the square root of 0 cubed. The square root of 0 is 0, and then 0 cubed is also 0. 1 to the 3/2 power would be the square root of 1 cubed. The square root of 1 is 1, and then 1 cubed is 1. (16 to the 3/2 power. This is a great example of why I like to do the roots first. The square root of 16 cubed. Remember, this is the same as 16 cubed and then take the square root. But if I were to do 16 cubed, first of all, is that a number that none of us know off the top of our heads? Probably not, okay? And so we have to take 16 cubed, and then I get some big number, and then I have to take the square root of that number that I'm not familiar with, okay? Here, do we know the square root of 16? Yeah, 4, right? And then 4 cubed is a lot more reasonable, I think, than 16 cubed. So we would get 64 here. You would also get 64 here, but this square root of 16 first is a little more accessible, a little easier for most of us. And then finally, g of negative 16. So this would be negative 16 to the 3/2 power, which would be the square root of negative 16 cubed. What can I say about this square root of negative 16? It's not real, it's undefined. Even if I switched the order on this and did negative 16 cubed to start and then did the square root, when I cube a negative number, I'm still going to get something negative out of that. So I still wouldn't be able to find the square root. It would still be something not real. For h, we have 8 to the 2/3 power, which I could also write as the cube root of 8 squared. So that would be the cube root of 8 is 2. 2 squared is 4. For k, this time we're plugging in for the exponent. So k of negative 1 would be 2 to the negative first. Remember, when I take a negative exponent, that's telling me to take the reciprocal. So this would be 1 over 2 to the first, which would just be 1/2. I would like you now to try the rest of h and k. For the rest of h and k. Okay, for h, 1 to the 2/3 power, that would be the cube root of 1 squared. The cube root of 1 is 1, and 1 squared is 1. Negative 1 to the 2/3 power would be the cube root of negative 1, then squared. So the cube root of an odd number is okay. We're asking what would you multiply 3 times? So this would be, in order to get the cube root of negative 1, I could do negative 1 times negative 1 times negative 1. When I multiply two of these together, we get +1. When I multiply by -1 again, I end up with -1. So the cube root of -1 is -1. That's parts of -1. And then -1 squared gives us +1. And then for our last one here, 125 to the 2/3 power, that would be the cube root of 125 squared. The cube root of 125 is 5, and 5 squared is 25. Again, a little bit easier to evaluate, especially when I've got a bigger number here, a little easier to evaluate usually the root first and then take the power. Then for k, plug in 3 for x. This would be 2 cubed, which is 8. And then k to the 1/2 would be 2 to the 1/2, which I could also write as the square root of 2. Can I simplify the square root of 2 to have a nice square root? No. So we could just leave it either as 2 to the 1/2 or the square root of 2. Those are both correct. They mean the same thing. On the next page, I'm going to do a little more practice with our exponent rules. For number 1, on page 7, I've got 4 to the 1/3 times 4 to the 5/3. I'm to start going to treat these just like they're x's. So if I had x to the 1/3 times x to the 5/3, I would add their exponents. I'm multiplying things that have the same base, so we add their exponents. 1/3 plus 5/3 would give us 6/3, and 6 over 3 is just 2. So if these were x's, I would end up with x squared here. When the base is a number instead of a variable, that does not change how we do this problem. This would just be 4 squared. I used exactly the same exponents. Since we're multiplying things that have the same base, all we do is add their exponents. Okay? When I add 1/3 and 5/3, we get 2. So this would be 4 squared. Since we can actually evaluate 4 squared, we know that we can simplify that to 16. If you gave me 16, that's fine. But notice I didn't change the base at all. Okay, I treated it just like it were an x. For number 2, I've got a power to a power. Again, we've got a number instead of a variable as the base for our exponent. That's okay. That does not change how I apply my exponent rules. These being fractions also does not change how I apply my exponent rules. So power to a power, I multiply. So I'm going to multiply 3/4 and 1/3. I can reduce my 3's here, and I get 1/4. So this is 6 to the 1/4. I didn't change anything about the way I did that problem. And then let's skip to number 4. Again, I'm going to think about this as if I had variables here. So where I have a cube root, instead I'm going to write this to the 1/3 power. Okay. And then since I don't see an exponent here, this means x is to the 1st power. Now, if I had x to the 5th over x squared, we would use our quotient property and subtract those exponents. So we would get x to the 3rd power. We're going to do exactly the same thing here. Since we have the same base and we're dividing, we subtract the exponents. So 1 minus 1/3 would give me 2/3. Thank you. If you need to rewrite these with the same base, you can, but 1 minus 1/3 usually isn't something that we get too hung up on. So this would just be then x to the 2/3. Now for this particular problem, my base is 3 instead of x, but that doesn't change the way I would do the problem. This would be 3 to the 1st over 3 to the 1/3. Subtract the exponents, and we get 3 to the 2/3. Notice the base for my exponent did not change. It's still 3. I did not do anything to this 3. It is the same 3 that was here and here, just like this is the same x that was here and here. Mm-hmm. Didn't you get the I made this up so we could talk about what the exponent rule would be there. Okay, separate side example. It did get kind of crammed in with the other one though. Okay, turn the page for me. We're going to jump again to page 8. The last thing I want to talk about for today is some more evaluating, but we're going to do this in a table. Okay, so table format instead. So I have some values of x selected here for you. What we're going to do is evaluate. So plug in our values of x to our function. So for f of x, we are plugging in our exponent here. So this would be 2 to the -2nd. Remember, for a negative exponent, that means take the reciprocal, move it to the other part of the fraction. So that's 1 over 2 squared, which would be 1 over 4. Two to the -1st, we would take the reciprocal, that'd be 1 over 2 to the 1st. So that'd be 1 over 2. 2 to the 0. What's anything to the 0 power? 1. And then 2 to the 1st is just 2. 2 squared is 4. 2 cubed is 8. Not too bad. Same idea for g of x, but be careful on g of x. Remember to follow order of operations, which says that we do the exponent before we multiply. So the last thing that we will do is multiply. So we'll start with 1/2 to the -2nd power. This tells me take the reciprocal, so that would be 2 over 1 squared. That gives me 4. 2 squared is 4. So then 10 times 4. Remember, the last thing I do is multiply by 10. 10 times 4 gives me 40. When our exponent is -1, this would be 1/2 to the -1st power. So take the reciprocal, 2 over 1 to the 1st power. That's just 2. So 10 times 2, which would be 20. I would like you to complete the table for g of x. Complete the table for g of x. So it says take the reciprocal. So if I've got 1/2 and we square it, right? Or take it to the -2nd, I should say. What I see every now and then is people want to say, well, just take 1 over 1/2 then, right? But like, when do we ever write like something over like a fraction in part of a fraction, right? Like that's a mess. I have to clean that up. I can't leave it as like a 3-level fraction. So when we take the reciprocal, that means we are switching the top and the bottom. Okay. So instead of writing this like 3-layered fraction, right? It's not a cake. I don't want more than 2 layers to a fraction. Cake, sure. Fraction, no. Okay. What I can do instead is switch the top and the bottom. That's what reciprocal means, is we're flipping it. And then when I flip it, that exponent is no longer negative. If you like, instead, you can apply that exponent to each part, like distribute it in. If it makes more sense to you this way, then do it that way. It means exactly the same thing. When we take 1/2 to the 0 power, we get 1. So then 10 times 1 is 10. 1/2 to the first power is just 1/2. So 10 times 1/2, or half of 10, would be 5. 1/2 squared would be 1 squared over 2 squared, which is 1/4. Thank you. So this would be 10 times 1/4. So that's 10 over 4, but we can reduce that to 5 over 2. And then 1/2 cubed. 1 cubed is 1. 2 cubed is 8. So we have 10 times 1 over 8. That'd be 10 over 8, which again, we can reduce. This would be 5 over 4. The trickiest part about GU is making sure that we saved the multiplication for the end and followed order of operations. Any questions for me on page 8? Okay. We're gonna stop there. And what I would like you guys to do now is go back and finish up those problems that we skipped on page 7. You do have some time right now to be able to work on those.